So I've got the great fortune that I've kind of transitioned now from my PhD to working with Celia on a great paediatric project. So Celia is a clinical psychologist in paediatric neuropsychology, qualifying with a doctorate from the University of Oxford in 2016. And she's been working looking at investigating network dysfunction following paediatric traumatic brain injury at Imperial College London and Great Ormond Street. And there's quite a large network which he's been instrumental in kind of setting up, linking together multiple different hospitals for looking at pediatric injury. So without further ado, Celia, I'll hand it over to you.
Hi, thank you very much. Can you see my slides?
Yes.
Yes, okay, brilliant. So thank you, Niall, for the introduction. So I'm going to share with you today some of the results from our research, which has been combining advanced neuroimaging and neuropsychology to learn more about outcomes following paediatric traumatic brain injury. And I hope that I can convince you of why this is such an important topic. So every year in England and Wales, 1.4 million people go to A&E following a head injury, and up to 50% of those are under the age of 15. So the major trauma pathways in the UK work really well, and we're saving more and more lives, but we need to improve the longer-term management of children once they leave hospital. So in the clinical neuropsychology service I work in, we see lots of young people who have had traumatic brain injuries, and thankfully, more often than not, they have been able to return to school, but are experiencing difficulties with the transition back to education. So they often report difficulties with keeping up in class, not being distracted by their peers, feeling really fatigued by early afternoon quite often, and some behavioural concerns that might not have been there previously. And this can be really puzzling, not only for the young person, but for their families and the wider system around the child, because the good physical recovery can often mask this ongoing need and ongoing disability. And a worry is that if the problems go unrecognised and unsupported, there's evidence to show that there are higher rates of psychosocial and interpersonal difficulties in adults who sustained a traumatic brain injury as a child, including higher risk of incarceration. So we really need to intervene early to ensure that a child's life trajectory is not negatively thrown off course by having a traumatic brain injury. So we know that some young people develop cognitive difficulties, but not all young people, and we think that it has something to do with the damage to the connections of the brain, so the white matter. So the reason that we're interested in white matter in particular, and Niall's talk was a brilliant lead into what I'm speaking about, is that the most severe traumatic brain injuries are when external forces placed on the brain cause this axonal damage or shearing of the white matter. And it's thought that this damage is an important marker of severity and outcome. So we use diffusion tensor imaging to calculate the fractional anisotropy value, which is thought to be a proxy for the health of white matter. So in healthy white matter, we expect most of the water molecules to be diffusing along the track in the same direction, and therefore higher fractional anisotropy values are indicative of better white matter integrity. So our research aims to better understand cognitive and behavioural outcomes after a paediatric traumatic brain injury by combining this information with studying the damage to the brain using advanced neuroimaging. Because we believe that improved diagnosis of the damage of brain connections in children is key to understanding their ongoing problems. And this will hopefully allow us to rapidly identify children who need help and direct them more rapidly to the appropriate neurorehabilitation and possibly guide the development of new treatments in the future. So our study was a cross-sectional study of 10 to 16-year-olds who were over 3 months post-moderate to severe TBI. We also recruited some age-matched healthy controls, and all of our participants came to see us for 2 study visits. The first visit to Great Ormond Street Hospital in London for a clinical neuropsychology assessment, and then a second study visit to Imperial College London for a brain MRI on our dedicated 3T MRI scanner. We were able to recruit 41 young people who had had a traumatic brain injury. And as has been shown in previous literature in this age group, we had more males than females, and the largest cause of traumatic brain injury were road traffic accidents, followed by falls, and then we had a few sporting injuries, some other that just weren't, that were some really kind of unfortunate accidents, and then some assaults. And so to jump right into the results, we completed a full clinical neuropsychological assessment with all of our young people. And what we found was that on measures of non-verbal and verbal general abilities, our traumatic brain injury group scored significantly lower than our healthy controls. And we also found differences on immediate and delayed verbal memory for story learning, but for the list learning, it didn't survive our multiple corrections. And in line with previous literature, we found group differences in processing speed. So with the traumatic brain injury group taking longer to complete timed tasks than our healthy controls. And we also found group differences in measures of executive functions. So our executive functions are a set of cognitive skills that help us to interact efficiently with the world around us. They encompass, for example, the ability to plan, to monitor, to control our behaviours, to problem solve, to inhibit socially inappropriate responses. And we found that children who had had a brain injury performed more poorly on these tasks. We were also interested in the parental report of what was going on for their child, and the measures of functional abilities, which are shown here on the top left, show that children with a traumatic brain injury were reported as showing less age-expected conceptual, social, and practical skills than their typically developing peers. And we also found that parents of children with a traumatic brain injury reported that they were having more difficulties with emotional control, behavioural regulation, impulsivity, peer relations, and also reported higher levels of stress. And we're clearly always interested in the child's voice in all of this. And so we gave some measures to our young people. And what's really interesting to note here is that children who had had a traumatic brain injury and those who hadn't didn't report significantly differently on the number of symptoms of anxiety, depression, and disruptive behaviour. But children with a traumatic brain injury reported feeling significantly more angry than their peers. And so now I'm just going to move on to talk about the results from the neuroimaging part of our study. So this is a figure showing the grey and white matter volume differences in our patients and healthy controls. The areas in blue represent areas of lower grey matter volume in traumatic brain injury patients, and the areas in yellow represent areas of lower white matter volume in our traumatic brain injury patients. And so what this is showing is real widespread abnormalities in both the white matter and the grey matter of the brains of children who have had a traumatic brain injury, reflecting a possible failure of these areas to continue developing as we would expect. And for the white matter, seen more clearly on the third and fourth picture across from the left, we can see significant reductions in the volumes of the splenium of the corpus callosum and more anteriorly in the frontal lobes. And then there are also more extensive areas of lower grey matter volume, most pronounced in parts of the caudate, which you can see on the second and third image across. So I'm just going to focus in on the caudate for now. So in adults, my colleague Sarah De Simone showed that executive function deficits following a traumatic brain injury were related to damage to the frontostriatal thalamic loops, of which the caudate is part of. And you can see in the top left image, I don't think you can see where my cursor is, but in the top left image, you can see the caudate subdivisions and the tractography analysis to join the white matter tracts with the anterior cingulate cortex. So because in our volumetric data of our paediatric patients, we could see clear changes to the structure of these areas, we were interested in looking at whether the same pattern emerged in the paediatric data. So what we found was a similar pattern of damage to the integrity of the same white matter tracts between the caudate subdivisions and the cingulate cortex, with lower fractional anisotropy in young people who had had a traumatic brain injury. So these are really preliminary results, but we are also seeing some of the same patterns of association between executive functions and reduced fractional anisotropy in our executive function in our white matter tracts. So the way the task is scored is different, which is why they look like there's a reversal in relationship, but actually they're showing the same thing. The greater damage to the white matter tracts associated with deficits to executive function. There's a bit more variability in our sample, so possibly due to the tracts not being fully developed in this age group, so we need to spend a bit more time looking at this, but from this we can hypothesize that the disinhibition and behavioural regulation problems that our young people are reporting may be explained by damage to these particular networks, which are thought to be important for the kinds of cognitive processes that underpin our abilities to perform these tasks of executive functions. And this is relevant in our understanding of outcomes after traumatic brain injuries, because it might help us to identify young people who are at higher risk of behavioural difficulties. And if we then are able to intervene and target these young people, we might be able to reduce the future risk of life taking a more adverse course towards the forensic system, for example. So now we're going to move on to the diffusion-weighted imaging. And so this is our whole brain skeleton of white matter tracts created using the mean fractional anisotropy values for all of our subjects. And this is shown in green. And then in areas in red represent the areas of lower fractional anisotropy in patients versus controls. And this is what I spoke about at the beginning, which is seen as a proxy for the damage to white matter structure. So lower areas, the areas in red, our findings are showing are areas of damage. So again, we're seeing really widespread areas of reduced white matter structural integrity in our young people who have had a traumatic brain injury, affecting a number of different tracts like the corpus callosum. And we're going to focus in on the splenium of the corpus callosum, which is the tail end of this large bundle of commissural fibres, and it's this inverted V shape under the ventricles that you can see in this image. So the location of the splenium is shown in the top left image in red, and the images below show one axial plane of the fractional anisotropy skeleton shown on the previous slide next to the same measure in adults who had had a traumatic brain injury, published previously in our group. And you can see a very similar pattern of damage, including in the splenium of the corpus callosum. There's evidence from computational modelling, and I think one of our colleagues at Mazdak Kajeri is going to present on this work later on in the day. So there's evidence from this work that the corpus callosum is an area highly susceptible to the rotational forces seen in some TBIs. So we hypothesised that these tracts might be at particular risk following traumatic brain injury, which is why we're consistently seeing lower white matter integrity. And work from our group has also consistently shown a relationship between the white matter integrity of the splenium and tasks of information processing speed. And in our paediatric dataset, we also found this relationship with lower fractional anisotropy being associated with poorer speed of information processing following a traumatic brain injury. And we don't see this same relationship with the healthy controls, so it does seem to be unique to our TBI group. And difficulties keeping up in class is one of the main complaints that young people and their families discuss with us in the context of education following traumatic brain injury. And so we can hypothesize from our findings that damage to the splenium of the corpus callosum may explain some of these cognitive difficulties. In clinical neuropsychology, we're able to identify these difficulties. We make recommendations, for example, if a child needs some extra time to complete their work. However, if this type of brain scan was offered as part of a routine follow-up alongside clinical neuropsychology, we might be able to identify children at risk of difficulties before the problems in school arise and before the child has started falling behind. So these are children who've often already missed a substantial amount of school. So early identification of the difficulties and early conversations with the wider system about what can be done to support the child would be preferable to the current timescale that we have for establishing support. So far I've presented whole group differences, but what's really exciting about this work is that it can provide information at the individual level. So my colleague Amy Jolly has developed this beautiful pipeline for processing the fractional anisotropy values of white matter tracts for a single subject against the group of healthy aged matched controls. So I don't have time to go into great detail with this pipeline, but what we end up with is this plot on the bottom left where the Z-scores of fractional anisotropy values for regions of interest of white matter for one single patient are plotted against our controls, and the patient tracts with significantly lower fractional anisotropy are then represented in red. So I've got two case studies to briefly illustrate why this might be interesting for clinicians and for researchers as well. So case one is a 16-year-old male whose traumatic brain injury resulted from a direct impact to the head playing sport. Initial CT scan showed a left extradural hematoma, which was surgically evacuated, and his post-op recovery was uneventful. He was discharged home on day 4. Our young person 2 is a 16-year-old female who sustained a traumatic brain injury from a road traffic accident. She was unconscious at the scene, and initial CT scan showed a subdural hematoma with midline shift. After acute treatment, which didn't include any neurosurgery, she was an inpatient for 6 months on a neurorehabilitation ward. So what we can see here is that for our young person 1 and young person 2, the T1 structural MRI scan, which is the one at the top left, doesn't add much to the initial CT report. So young person 1 has focal injury, young person 2 has nothing of note. The susceptibility weighted imaging scan, which is the one on the same row just across on the right, however, show a different picture and show that young person 2 has evidence of microbleeds or traumatic vascular injury, which are not present in young person 1. And then if we move down a row and we look at the DTI, the diffusion tensor imaging diagnostic classification, we can see that again, young person 2, so the person on the right, has multiple white matter tracts that are significantly different to controls, whereas young person 1 does not. And what's really fascinating is that this correlates with their cognitive outcomes. So young person 1 didn't score differently to controls, whereas young person 2 had significantly lower general abilities, speed of information processing, and parental reports of higher impulsivity and aggression. And so if we think back briefly to the few slides before, looking at the association with the splenium and processing speed, this is shown really nicely here. So the corpus callosum splenium is the third tract across from the left. And young person 1 has no difficulties in processing speed and no significantly reduced fractional anisotropy on the splenium tract, whereas young person 2 has poorer performance on processing speed measures and reduced fractional anisotropy in that splenium tract. So this highlights the clinical utility of these advanced neuroimaging techniques at the individual patient level, and I think it could also be really powerful information to give to families to help them understand the ongoing difficulties, because it's all too often that we meet patients who've been told that their MRI scan is fine, and therefore this suggestion is they shouldn't still be struggling. And what we're showing is that routine structural MRI scans are not enough, and in order to really understand a person's ongoing difficulties and outcomes, we need to offer advanced neuroimaging in combination with this clinical neuropsychology. So just to round up, we found extensive neuropsychological and neuroimaging whole brain group differences in the grey and white matter structure of our young people who had had a traumatic brain injury. And when we combined these techniques, we found that there was impaired executive functions associated with the frontal striatal white matter tracts and impaired processing speed, which was associated with the white matter integrity of the splenium. And I hope that I've also shown that this has the potential to be useful clinically at the individual level and provide young people and the wider system around the child some really important information and novel information about their ongoing difficulties. So I'd just like to say thank you to the Paediatric Traumatic Brain Injury Research Team across Imperial College London and Great Ormond Street Hospital, and all the team at C3NL and the clinical neuropsychology team at GOSH, the patient identification centres and charities who were amazing and helped us so much with our recruitment, our funders, Action Medical Research for Children and Great Ormond Street Hospital Charity, and most importantly, the young people and their families who took part. And we asked our young people for feedback, and in answer to the question, what did you learn taking part in our research? One young person said, how complicated it can be bumping your head. So thank you very much.
Great, thank you, Celia. That was an amazing talk, and I think you kind of really highlighted a lot of issues very well there. So there was a few questions here. So one is asking, how do you separate out executive function difficulties from processing speed if using executive tasks where the score depends on time taken to complete the task? So this is something that I feel a lot of people have difficulty with within assessments.
Yeah.
So what are your thoughts there?
Yeah, absolutely. So I think that's why batteries like the DKEBs in particular are quite useful, because they have 4 different subtests. And so what we're doing in our analysis going forward is making sure that we account for the first 2 subtests that are processing speed, and actually minus those from the executive function subtest, so that we can be sure that it's not just a measure of processing speed. And I think it's really important also to look at the verbal and non-verbal measures, because then we can be sure if the person has ongoing difficulties, for example, with these particular measures, that we're, kind of casting a wide net in what we look at. But yeah, it's a really good question, and it is something that we account for in our analysis.